In this video, we'll discuss about maximum width ramp. So first, let's understand the question. A ramp in an integer array nums is a pair I, j for which I is less than j and nums of I is less than equals to nums of j. The width of such a ramp is j minus I. Given an integer array nums, return the maximum width of a ramp in nums. If there is no ramp in nums, return 0. So what they're saying is that you are given an integer array in your input and you need to find the maximum width of a ramp. Now, what is a ramp here? That for any pair I, j, like for any two numbers with the indices as I and j, where I is less than j, then for any such pair, if the nums of I is less than equals to nums of j, then it is a ramp, right? Then it is a ramp. And what is the width? The width will be, width has j minus I. Okay. So you need to find such a ramp from this array whose width is the maximum. And whatever is the maximum width that you need to return. Right? So basically, if you see here, for any pair I and j, where I is less than j, and nums of I is less than equals to nums of j, that is a ramp and its width is j minus I. So let's suppose in this array, if you see that this 6 and 8, right? What is their indices? 0 and 2. So is 0 less than 2? Yes. Is nums of 0 less than equals to nums of 2? That is 6 less than equals to 8? Yes. So then that means this is a ramp. Now what is its width? J minus I. That means 2 minus 0. That is 2. 2 is the width of this ramp. So in a similar fashion, you need to find out a ramp whose width is maximum. So the brute force here can be that you check all the possible pairs. For all the possible pairs, you check this condition, you find out their width and whichever is the maximum width that you need to return. Right? So you will just loop from I equals to 0 till n, and then inside this you will loop from the next element. So j will be I plus 1 till n. And then you will check that if your nums of I is less than equals to nums of j. Then let's suppose you have taken a maxi variable, so you will update that. Max equals to max of maxi comma j minus I, right? So this is what you will do, and at the end you will return maxi, right? So with this, you are finding out all the possible ramps that exist in our array, and then you are finding out the maximum width and returning it. So this although will give you the answer, but if you closely look here, this loop is running from 0 till n. That means n times. And inside every iteration of this loop, this will run from I plus 1 to n times, meaning n minus 1 times, right? So this was n times and this was n minus 1 times. So the time complexity of this will be big O of n squared, which is too large because n is given to us 10 to the power 4, right? So n squared won't work. It will give you a theory here. So now, how can we approach this problem? What can be a better solution? So if you see that, what are we doing? And for every index j, we want all the indices I. Since I is less than j, then that means whenever we are considering j, we will consider only the elements which are on the left side of it, right? Because I is less than j. So for any element at index j, if we have all the elements which are smaller than this, smaller or equal to than this, then we can compare them together, right? So for example, this 5 can form a ramp with how many elements? Whichever elements. So if you see, this 0 is less than 5, 2 is less than 5, and 1 is less than 5, right? Then that means 5 can form a ramp with these three elements, right? If I write here, so 0 and 5, 1 and 5, 2 and 5, right? These can form a ramp. But now if you find their width, so 0 and 5 were at index 1 comma 5, 1 and 5 are at index 4 and 5, and 2 and 5 are at index 3 and 5. So now what will be their width? J minus I. So this will be 5 minus 1, which is 4. This will be 5 minus 4, which is 1. This will be 5 minus 3, which is 2. So that means for 5, we could form these many ramps, and out of them, these are their widths, and this is the maximum. Now, if you closely look, can you find out a hint here? Whichever is the element which is farthest from 5, out of these, whichever was the element which was farthest from 5, that only will give you the maximum width, right? Because whichever is the farthest, that will have its I value smallest in comparison of all others, right? That is why that will give you the maximum width. In this case, you saw that 0 is the farthest element here and 2 and 1 are closer. So that's why when you calculated the width of this ramp, it was maximum out of all, right? So then that means if somehow for every element, I know which is the smallest element, okay, which is the smallest or equal element than this to the left of it, then I can form a pair of this with that element and I can find the width. And if I do this thing for all the elements, at the end, I will be able to get the maximum width ramp, right? So what are we going to do is, we'll start from the starting of our array and we'll keep track of what is the minimum element till now. So when you will start, we have considered this much array till now, right? So for this, what is the smallest element? 6. So we'll store it here. I'll write index also 0. So this index is similar to what index is here. Okay. Then we'll consider this much array. Now in this much array, which is the smallest element? 0, right? So we'll keep 0 here and its index, which was 1, right? Then we'll consider this much array. Now here, which is the smallest element? 0. 0 we have already written. Then this much array, again 0 is the smallest element, we have already considered. Then this much array, again 0 is the smallest element, so we have it here. Then for this much array, which is the smallest element, 0, we have stored here, right? So we have traversed the entire array and we have find out all the smaller elements in decreasing order, right? Since at every point we are checking that whichever is the smallest element and that we are putting here. So when this will be formed, it will always be in decreasing order, right? Now, when we have the elements, now when we know that what is the smaller element to the left of my elements, because I started from the left, right? That is why I'm saying that whatever are the smaller elements to the left side that I have here, right? So then that means whatever can be my valid I indexes that I have stored here, now I just need to pair them with the jth indexes, right? And j is greater than I, so we'll start from the ending. We'll start from the right and we'll move on to left and we'll keep on comparing, right? Now when we saw here that when we were at 5, it was better if we could pair it up with 0. Why? Because for others, it was giving smaller width. We wanted to compare this 5 with the smaller element which is farthest from 5, right? So now if you see here, we have 0 stored here, right? When we traversed in this array and we stored the smaller elements, then whichever is the smaller element as compared to 5 to the left of it and whichever is the farthest, that will be stored here, right? So we'll compare these two. We will when we are at here, we compare this with this element, with the smallest element till now in this array, right? So we'll compare these two. Now I said these are going to be my I indexes and these are going to be my j indexes, right? So what we need to check that nums of I should be less than equals to nums of j, right? So we'll check that. Is 0 less than equals to 5? Yes, it is. Then what we'll do? We'll calculate its width because this is a valid RAM and width is j minus I. So we will do 5 minus 1 which is 4. So 4 is one of the widths that we have got. Right? Now we'll remove this. We will not consider this further. Now why we are removing it? Why we are not considering further? Because if you will see for 1 also, 0 is the smallest element to the farthest of it. For 2 also, 0 is the smallest element farthest to it, right? If we'll remove it from here, then we won't be able to consider these RAMs, right? So there is also no need to consider this. Why? Because when you have considered 5 and 0, these were farthest from each other, right? What was there in this is 5 and 1, which difference was 4. This gave you the maximum width. Now, if you compare these also, then it will be 4 and 1, right? So, 4 minus 1 will be 3. Then if you compare 2 and 0, so it will be 3 minus 1. So, 3 minus 1 is 2. So, if you will see that, again, these are smaller widths as compared to this because these are farthest from each other. So this width will always be the maximum. So if you will compare these also, anyways you will get a width smaller than the one which you got from here. So there is no point in finding out the width for these RAMs also, right? So we'll just remove this 0 from here. Okay. Now we'll check for 5 again. Now for 5, we have 6 here. Now, is it satisfying the condition? Is 6 less than equals to 5? No, right? So now we'll come here. We'll come at this number. Now we'll check, is 6 less than equals to 1? No. So we'll move here. Is 6 less than equals to 2? No. Then we'll come here. Is 6 less than equals to 8? Yes, now it is. So now you will find their width. So what will be their width? 2 minus 0, which is 2, right? And since now you have formed a valid RAM, we will remove this also, right? Now you will check for this. Now for this 0, we don't have anything here. For the 6 also, we don't have anything here. So now we will stop. Now at the end, when you traversed in this entire arrays, you got these two RAMs or these two widths of the RAM, right? So whichever is the maximum out of it, that will be your answer, which in this case is 4, right? So what we did was, for this array, we found out that at every index, right, array starting from 0 till that index, what is the smallest element? And whichever was the smallest element, we kept on storing here. And because when this is compared with some other index and we have got a valid RAM, we don't have to compare this particular number with other elements. And that is why we are storing this 0 only once, not for all the indices, right? And then what we did was we started from the end of this array and we compared the last element of this array with this. And we checked that if it is less than equals to, right? And if it is, then we remove this last element, right? Now, what are you going to use for this particular thing? When we are finding the smaller elements, which data structure you will use? Now, if you closely look here, we are always considering the last element, right? We are always comparing the last element with this element. And whenever we have found out this condition to be true, at that time we are always removing the last element, right? So that means we are always accessing the last element and we are always removing the last element, right? So which data structure follows this principle? That is stack. It follows LIFO principle. right? So here we'll always have the access to the topmost element, and we can always pop out the topmost element. That's why we will use a stack to store these elements, right? And since I told you that these elements will be in decreasing order, why? Because at every point we are checking which is the smallest element. So these numbers will always be in decreasing order. So this will be a monotonic stack. What is a monotonic stack? Where the elements are stored either in increasing or decreasing order. Since here the elements will be stored in decreasing order, we can say that it will be a monotonic stack. So now what are we going to do is, first of all, we'll create a stack, right? Which will be of type integer st, right? And now let's suppose this is our stack, or I will keep it a little right. This is my stack st. Now we will have to update the smaller elements in our stack, right? So we will loop from I equals to 0 till n. Now if my stack is empty, right? Then that means I'm at the first index, and at the first index I only have the element 1. Like I only have one element. I cannot compare it with others. So this will be my minimum element till now, right? So I will store 6. Now if you closely look, when you will start from the right side and you will compare this with the value which is present at the top of my stack, you will have to compare their values, and if it is a valid ramp, then you will have to find out the difference between their indices as width, right? So if you will store the element here, then you don't know what is its index, and you will have to traverse this entire array to find out the index of 6, right? So instead of storing 6, we'll directly store its index. So the index of 6 is 0. So we'll store 0 here. So now whenever you have to compare the values, then you will do what? Nums of stack.top, right? That case you will get 6. And whenever you want index, then you can directly do stack.top, which will give you 0. So in our stack, instead of elements, we will store the index. So if your stack is empty, then we'll directly push the element, push the index. So st dot push I. Now there will also be one more condition in which you will push the index. So that's why I have kept it like this. Now when you will come here 0, now this 0 is less than 6, right? This 0 is less than 6. The element which is present at the top, it was 6, right? So 0 is less than 6. We have got one more smaller elements. So in that case also we will push, right? We will push the index. The index of 0 is 1. So we will push 1 here. So our other condition will be that if your nums of I is less than nums of st dot top, then in that case also you will push, right? So after this 8 will come. Now 8 is not less than 0. This value is 0, right? So 8 is not less than 0, 2 is not less than 0, 1 is not less than 0, 5 is also not less than 0. So at the end this will be our stack, and this loop will be completed, right? Now we have to start from the ending, and we have to compare these elements with the top element, and we need to find their width, whichever is forming a ramp. So we'll create a variable max width to keep track of the maximum width, and its initial value will be 0, right? Now we will loop for j. We have got our I indices. Now we will loop from j from the ending. So we'll start j from n minus 1, and we'll move all the way till 0th index, right? Then we'll check while our stack is not empty, right? While our stack is not empty, what we were doing, we were comparing this and this, and if this value was less than equals to this value, then we were checking the width, right? So while our stack is not empty and nums of st dot top is less than equals to nums of j, then that means they are forming a ramp, a valid ramp. So we will find out the width and update the max width. So max width will be equals to max of max width, comma, what? J minus st dot top, right? Because at the top we have stored the index. And then we will pop this element out, right? We will pop this. So this will be our loop. And at the end, we will return max width, right? So if you see here, when you started, the value of j initially will be what? We had the number of values were 6. So the initial value of j will be 5, right? 6 minus 1, 5. So now you will compare the top elements. So our stack is not empty. And what is st dot top? It is 1. So nums of 1 less than equals to nums of 5. What is at nums of 1? 0. And at nums of 5? 5. So is 0 less than equals to 5? Yes. So we'll come here. Now here the max width value is 0. So now we'll calculate this. J is 5 and st dot top is 1. So 5 minus 1 is 4 and max width is 0. So maximum of 0, 4 is 4. So now your max width will be updated to 4, right? And then next we have st dot pop. So this will be popped out, right? Now again our stack is not empty. Now we'll check this. So nums of st dot top is 0 less than equals to nums of 5. So nums of 0 is 6. So 6 less than equals to 5? No. So we will stop here, right? Now our j will decrement to 4, right? Now we'll compare it. So our stack is not empty. St dot top is 0 and nums of 0 is 6. And nums of j is what? Nums of 4. So that is 1. So is 6 less than equals to 1? No. So now our j will decrement to 3. Now stack is again not empty. St dot top is 0. Nums of 0 is 6. And nums of j, that is nums of 3, which is 2. So 6 less than equals to 2? No. So we'll stop here. Then our j will decrement to 2. Now nums of 0 is 6 and nums of j, that is nums of 2, is 8. Now is 6 less than equals to 8? Yes, it is. So now we'll come inside. Now here our j is what? 2 and our st dot top is 0. So this is 0 and our max width is 4. So maximum of 4 comma 2 is 4 only. So our max width will be 4 only. And then we'll do st dot top. So this will also be popped out. Now our j will decrement to 1, but our stack is empty now. So it won't go inside this. Then j will be decremented to 0. Again it won't go inside because our stack is empty. And then j will become minus 1 and our loop will stop here. And at the end we will return the maximum width, which is 4. Right? So I hope you got it. So now let's code this out. Right? So first of all, we'll create a variable n which will store the size of my nums vector. Then I'll declare a stack st which will store the indexes. Then we'll loop from the starting, that is from 0 till n. And we'll keep on updating the smaller elements in my stack. So if my stack is empty or my nums of I is less than nums of st dot top, then in that case I will do st dot push I. I will push the index. So now I'll get my stack filled with the initial values. Now we create a variable max width which will store the maximum width, and then we'll start j from the end. So j will be equals to n minus 1 and it will go till 0. So we'll do j minus minus. Then we'll check that while our stack is not empty, right? And your nums of st dot top is less than equals to nums of j, then you will update your max width. So max width will be equals to max of max width, comma, j minus st dot term, right? And then you will pop this element away, right? And at the end, you will return max width, right? Let's run this. So our test cases are accepted. Let's submit this. So it got accepted. Thank you so much for watching.